The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Ladies and gentlemen, hello and welcome back to another episode of Future Proof. Your host, Eric Kavanagh here, and I am so excited to have several experts with us today. We're going to talk about the language of artificial intelligence. Yes, there is an actual language for artificial intelligence. It's a programming language called Julia. For those of you familiar with Jupyter Notebooks, J-U in Jupyter comes from Julia. Not a lot of people know that, but Julia is a fascinating computer language. And with that, I'm going to hand it off to my guests. We have Viral Shah, we have Edelman and Keno Fischer on the line today. I think Viral is going to be doing most of the presentation. So Viral, I'm going to hand it off to you.
Yeah, thanks, Eric. Great to be on the program here. And, I'm just sort of going to walk through this presentation, and if we can, do a Q&A, and I'll have everyone jump in. So, Julia is a language for AI, and why is that so? I think in order to answer that question, we should jump into why the Julia language was created in the first place. If you've sort of looked at the last 25 years, we've had so many different programming languages, and the general trend has been that you always have to write every program twice. You first sort of write, you have the rough idea. It's sort of the pen and paper equivalent of things that, when a specialist has an idea, whether they are a financial quant or an actuary or biologist or physicist, they actually write their algorithms out in a language like Python or SAS or MATLAB, which are easy to work with, but are not high performance. And then they rewrite them to put them into production using C, C++, C# or Java. And so you end up almost writing every program twice. And it turns out that, hey, what if you could just write it once and, have the ease of use and all the simplicity and fun of writing simple mathematical code, but then press a button and run it on a supercomputer or whatever be the hardware of your choice in one shot without having to rewrite it. That was sort of the reason, why we created Julia, that we were sort of tired of having this, dichotomy between you can either have performance only or you can have productivity only, but not both at the same time. And it was called the two-language problem, and Julia is the first language to solve the two-language problem. So, Julia started out with the four of us. Alan is on the line here with me. You can see him. And then we had Jeff Bezanson and Stefan Krupinski. Keno joined us a few years later when we started Julia, but Julia started life about 10 years ago. Stefan and I were throwing a frisbee around in Santa Barbara, and we were discussing the need for a new language. We started an email conversation with Alan and Jeff, and in the first couple of days, we actually had the first working Julia interpreter out there. It took us 3 years to get the first announcement out, so that was 2012, and in the very early days, Julia became the JU in Jupyter. So in 2013, Julia became the JU in Jupyter. It was the second language to be added to Jupyter after Python. This was sort of also about the time when Keno had joined the project. Keno was actually just finishing up high school and entering Harvard University at that time, and he is such a talented contributor. He ended up joining the community in a big way, making Julia work on Windows. And then we all co-founded Julia Computing together in 2015. This was when the first early commercial users started using Julia, and AI kind of had been sort of developing in a very interesting way over these years. And that's sort of, I would say 2015 was when AI started entering the limelight. 2017, Julia got to about 1 million downloads, and 2018, which is 9 years after we launched the first project, the first work on Julia, we released Julia 1.0. And just a few months ago, we hit 10 million downloads. The four of us were awarded the Wilkinson Prize. Alan received the Sidney Fernbach Award for his contributions to Julia and parallel computing. Keno was chosen as the Forbes 30 Under 30 in enterprise technology. So it's been quite a wonderful ride so far. And it's been 10 years since we've been working on this. But if you're familiar with programming languages at all, 10 years is how you get to the starting line. Now, one of the things that's most interesting about Julia, and this is where I'd like Alan to sort of jump in, is how closely Julia is, related to the underlying mathematics that people write in it. And I have some, stuff on this slide that shows the beauty of the native mathematical operators in Julia. So, Alan, do you want to maybe talk a little bit about that?
Sure, I could say a couple of words, but I guess we'll keep your slide. So I'm constantly showing how Julia just looks like the math. I like to tell people that when I look at a lot of other programs, I might see a variable called alpha, and it'll say ALPHA or beta, BETA, sometimes in capital letters like old Fortran days. When you know what these math symbols mean, you could very quickly just look at the thing and say, I know what's going on, as opposed to kind of having to read hard code and try to figure out what it's doing. And so we like to say that that the math is the software is the math. It helps for coding, it helps for getting good algorithms up, and it just helps for the reading and the beauty of it all.
When I remember from years ago when I was a kid, in fact, I learned programming in BASIC when I was 12 or 13, and I recall the mathematical functions where you wanted to add 1 to a variable. If the variable was A, you would write A equals A plus 1. Well, in math, that doesn't make any sense. A equals A. And so you guys, that's a very simplistic version of what you're talking about, but what you guys did is set out to create a language in which the operators do exactly what they're supposed to do. I think a lot of people who don't know programming won't realize that, but it's actually a very big deal if you're trying to do some data science, because if you get something wrong, you get error propagation and your whole project is on its side, basically. Did you talk about why it's important that the operators do what they're supposed to do?
Yeah, so, if you look at sort of this slide here, right? So, when you want to calculate the square root of 25, you use the mathematical square root symbol. So, a data scientist who's used to, who's had a training in mathematics, maybe they attended Alan's lectures at MIT, and that's how they got trained. And, Alan would have not told them to write SQRT 25. You'd have taught them to use the square root symbol and 25. And in Julia, you write exactly that. So it helps your code look exactly like, your research or your algorithm or the data science, technique that you're using, that when there is one-to-one correspondence between your algorithm and your code, the chances of errors, like you mentioned, are minimized, and chances of getting things right make sense. Also, what's very important in programming is not just writing programs, but also reading programs. So when you read programs, if the symbols have their usual meaning, the way you were taught, in middle school or in high school or college, it's just that much easier to read a program.
Let's say you buy something. I'm getting things from Amazon all the time at my front door, and it has instructions that are mainly words and no really good diagrams. You just start wondering, what does this thing mean? Like, wait, which part goes into what part, right? And, but if you have that really clear diagram, you know what everything is. And so that's kind of what we want with the math. And a second point I'd like to make is not only do people write code and read code, but also if we're trying to do what we're doing here, which is to create communities that write code together. So it's not just one person sitting at a desk writing code, but somebody might be here where we are in Massachusetts, and another person might be over in London or wherever in the world. The sooner the person can actually know what's going on, the faster they can join in the fun and work together.
Yeah, that's a really good point I'll throw out to our audience, because to Alan and Viral's comments there, code is not just to be written and, of course, compiled and used and run, but you want other people to read that code and understand it, whether it's a new member of the team, whether someone retires or quits or just goes away. The point is that if you can understand quickly what the code is doing, that greatly facilitates time to value, time to production.
So, Alan, you might want to, say a little bit about why mathematicians love these kinds of operators. And this is only a small selection of operators that we have in Julia today. I just wanted to sort of put this up out there for people to see, the richness in mathematics and how that is mirrored in Julia. And Julia is probably the only language that does that. But I just wanted to point out that there's over 10,000 companies using Julia. There's close to 500,000 Julia programmers out there worldwide. And the Julia community has put together 3,000 open source packages. Before we jump into sort of the whole discussion on why Julia is a good language for AI, is all the universities out there teaching Julia, and the MIT out there is naturally Alan. You've been teaching Julia ever since 2011, I think. Do you want to maybe say a little bit about that?
Yeah, I think that's probably true. So I was using Julia in a graduate course in the early years, and then it sort of gradually moved down the curriculum. So I'm a professor at MIT. I'm in mathematics and I'm in the computer science and AI laboratory. Just as the whole COVID-19 thing was happening at the beginning of March, we were also set to teach a Intro to Julia course. And very quickly we decided that we were going to turn this class into an introduction to computer science, where we also teach computational thinking related to COVID-19. And the class is online. If people want to look at it, they can actually watch the videos online. We taught this class. A lot of my colleagues would say, like, oh, you teach them the math on the blackboard and then you code it up for homework or something like that. Doing it hand in hand the way we did it, the students loved it. They built everything up from scratch and everything performed very well. They just really enjoyed it.
So, this is great. So Julia is, high performance. It's you can write all your beautiful math in it. You can, run it on large supercomputers. How does all of this relate to AI? So Keno has been, leading some of our charge on the AI side of things. Keno, do you want to say a little bit about, what's going on, on the next few slides?
Yeah, sure. So I think there has been a real big change in thinking over the past couple of years. We sort of saw ImageNet, which is the big image recognition benchmark, start to actually approach levels where it was interesting. For that, I mean, we've had neural nets since the 90s, but it never really approached the point where, you could feed an image to a computer and it could tell you with any sort of accuracy what was in that image. So, that didn't happen until the early 2010s with the breakthrough in ImageNet that I think really sparked this interest both academically in using neural network-based techniques, deep learning-based techniques for a huge variety of problems. With those challenges, there comes software. So TensorFlow. So what those frameworks tended to do was be very, very focused on, okay, we just want to be able to do machine learning, deep learning, and just did whatever had to be done to get that done. But then people realized, and not just us, but a bunch of the people that Viral listed on the slide, Jan LeCun, one of them, all of these people really realized that the real innovation is not necessarily neural nets. The real innovation is that we can use computers to optimize other computer programs, to optimize models, to create something that we tend to call differentiable programming, where rather than having a neural net, you have an actual program that you then feed into the same techniques that were used to optimize something as simple as an ImageNet model, but actually optimize the entire program by taking a derivative of the program and then feeding that into a general purpose optimizer. So that sort of only really started happening maybe in the last 3 or 4 years, but that's really where we're trying to go with Julia. Is like you have an arbitrary Julia program, you should be able to feed it to a differentiable programming system and get it to optimize the parameters of that program according to your data. So so this is some work that I did. So a lot of people may be familiar with Jeff Dean, who's one of the very senior engineers at Google. There's a lot of jokes online about him. Sort of Jeff Dean being the Chuck Norris of software engineers. Some of you may have seen those. But anyway, he's a fantastic engineer, and Google has this hardware called TPUs. So about a year and a half ago, I did some work with Google on getting Julia to run on TPUs. And it was actually kind of easy to do because in Julia, we are separating out all these abstractions. So the building the model and building the program is totally separate from the part that runs on the hardware. So it was really easy to just rebuild the part that runs on the hardware while keeping everything else, which made it a lot faster to do in Julia. And I'm very glad that Jeff Dean approved after we published that work. And I think we talked about that actually with you, Eric, on the radio show at the time. about what TPUs mean and sort of the difference between TPUs and GPUs. But
we all know what a CPU is, that those are the traditional old-fashioned processors. And then GPUs, of course, graphical processing units, became very popular because of gaming. And then we learned that, guess what? GPUs are great for parallel processing. And so they wound up being used heavily for analytics and neural networks and so forth. But then Google comes along and designs TPUs, TensorFlow processing units. Can you explain to the audience what's different about a TPU, like in its actual architecture? What's different about it, and why is it different? And what does that mean?
yeah, so in chip design, you always have this trade-off between generality on the one side, and then performance or power usage. As these neural networks became more popular, Google and a bunch of other hardware companies sort of realized that the precision that these GPUs had were exceeding what was required to get these neural networks done. So, there's common data formats, but you generally grade them by like bit width, and GPUs can do CPUs generally all 64-bit, GPUs generally half as wide, though some of them can also do 64. But it turned out that for things like machine learning, you could actually get away with just making a ton of really, really small execution units. The neural networks rely on a ton of really, really small individual steps of computation that are then chained together. Basically, what these hardware companies, including Google, realized was that it was overkill to use something like a CPU core or even a GPU core to do these really small bits of computation. So if you make a specialized chip, you can get a lot faster execution at the trade-off of being more specialized to these kinds of artificial intelligence, machine learning workloads.
What Keno described is what is generally referred to as differentiable programming. The standard deep learning tends to be a bit brute force. So Microsoft just announced this mega supercomputer that they built for OpenAI. So, but these things use a huge amount of power. But one of the things that that we in the Julia community realized is that a lot of problems do not start out with brute force. There are a lot of scientific problems that could benefit from AI, but we already understand the world of science around us. We understand Newton's laws, and we understand the laws of thermodynamics, and we understand a lot of different things about various different scientific phenomena. So, if we can combine the data that we gather from our experiments with some of the AI methods in, that Google and Facebook and all these companies have sort of put together for us, you really can combine science and AI into a sort of a combined field called scientific machine learning. And because you're now bringing your intuition about the world at large into your AI computations, you do not need a supercomputer necessarily. You could work with a much smaller amount of compute and still get more meaningful answers that are explainable, that are relatable, that regulators might be happy with, for example, and so on and so forth. And that is largely sort of what the field of differentiable programming is all about. And what do you need for differentiable programming? You need something that is fast, something that is easy, good with mathematics, runs on large supercomputers, works on GPUs, your graphics processing units and TPUs that Keno just explained, runs on the cloud, and is easy to work with. And Julia is the only system out there that can do all of this stuff today. And this is why Julia is very quickly becoming the language of AI. So, with that, I think what might be useful is talking about some of the applications that Julia has been used for. So Aviva is one of the world's largest insurance companies, and they use Julia for doing 1,000 times faster insurance modeling. They replaced a whole data center worth of hardware with 5 simple computers on the cloud. Just by switching to Julia, they got this amazing speed up out there. The New York Federal Reserve Bank uses Julia for building models of the economy, while BlackRock uses Julia for their analytics platform. So the world of finance uses Julia a lot today in order to do various kinds of financial calculations. This is actually a machine learning calculation that Keno did. Keno, do you want to talk about what exactly this is?
Absolutely. So this is basically what this is. It's a project out of UC Berkeley in collaboration with the Lawrence Berkeley National Laboratory. So what this project is taking all the astronomical images that we have from survey telescopes. So the point of these survey telescopes is to find out what's out there, such that then you can go back and look at them with one of these more specialized telescopes. The Celeste project was, we have all this survey telescope data, tens of terabytes. How do we actually process this data? Because it's very non-trivial to do, because a lot of the stars and galaxies will be near the detection limit of what these telescopes are capable of. But those stars and galaxies might be some of the most important ones. So, what Celeste did was, it's sort of, the statisticians at UC Berkeley came up with this very rigorous Bayesian machine learning model that could tell you not only, okay, is this most likely a star, is this most likely a galaxy, but how certain are we that it's a star? How certain are we that it's a galaxy? So somebody designing an astronomical observation might say, okay, I want to look at 100 stars that have these particular properties. So with Celeste, the output that it produces, they would be able to go through this catalog and select, according to probability thresholds, according to whatever their criteria are, some targets for further observation.
So why did this thing need a supercomputer?
There's two aspects. One is it's a huge amount of data. Even the amount of data that we had access to, which was sort of last generation survey telescopes, was about 55 terabytes of data. But the computation itself is also really, really tough, because not only do you need to process one image, but you need to align all these images, and then you need to run a big machine learning problem on it, and then you need to do sort of a global optimization. But the point of doing it on a supercomputer was to prove out that sort of for next generation data, we wanted to show that it was possible to do on current generation hardware to process the entire data set in a reasonable amount of time, even when the new survey telescopes will be coming online in the next year or two.
So, I thought this would be a good point for Alan to say a little bit about, why Julia makes parallel computing that much easier than everything else out there.
I've been interested in various kinds of high-performance computing since I was a graduate student, probably moonlighting to earn a little bit of money at a company called Ticking Machines. They made the connection machine that was very popular in the day, but I think nobody under the age of 40 has ever heard of it. But it was famous for being the best-looking supercomputer. So in any event, lots of people want to accelerate their computation. It's always been a tricky problem to figure out how to make best use of the hardware. It's much more than an algorithmic problem. It's an engineering problem. There are a lot of issues, and there have been a lot of people who've tried to make this easier, to make speeding up programs easier, and there haven't been that many really satisfying solutions to date. And Julia is, in a way, we created Julia to hopefully become the solution to this big, complicated problem. And Julia is already showing that it can do this, that ultimately what you'd like to do is write a program, and if you write it in a certain kind of way, maybe with no changes or small changes, you'd like to be able to run it on very large supercomputers like the ones that Keno described, or on GPU or TPUs, and you'd like them to just run. This is the sort of productivity problem that we'd like to be able to do. And I see Viral's slide there, and I can tell you right now that there's a good story about some of the heaviest users of supercomputers. They're the people who are working on the climate. They're working on climate models, and so this is probably climate modeling is probably arguably the most important problem of our time. COVID-19 may be the most immediate one, but climate modeling, the climate global warming may well be the big problem that hits us a few years from now. And so what happened was, some of my colleagues at MIT came over and said, you know, we used to write all these programs in Fortran, and then we started using Python and this and that. We're thinking about throwing away all our old programs. They're just not flexible enough. They can't do what we want. We want to use Julia. Don't talk us out of it. And what they did was they said, but we have to check the performance first. What we would like you to do is they gave us a little snippet of a program. And they said that if you can make this program run fast, you know, and they gave us 3 weeks. They were very generous. They said that it doesn't even have to be faster than their current version. If it's within a factor, if it's 1/3 as fast, they said they'd be happy. Well, we worked hard for 3 weeks, and we brought them all in, and we showed them the factor of 3. We were 3 times faster with Julia. And the code was like this long, as opposed to, you know, way big, you know, all the things that make Julia very special.
And it's interesting to point out that, you know, in these climate simulations, we are now being able to use AI techniques. There's a scientist at MIT, Chris Rakakis, whose research is the scientific machine learning, and he's applying those methods into accelerating these scientific machine learning models in climate simulation to the extent that they are thousands of times faster than the earlier simulations that people were running. Another fantastic area where Julia has been you know, used very successfully is in the area of personalized medicine. We have been working with in the School of Pharmacy at the University of Maryland in Baltimore, and put together a beautiful package that allows Julia-based algorithms to pick the perfect dosage for you when you're undergoing treatment at a hospital. Companies such as Pfizer are using Julia to build, you know, much faster simulations, you know, when they design new drugs. Genentech, for example, used Julia to build, you know, to accelerate an R code by a factor of 65,000. And, you know, this is not something that's just 5 or 10 times faster, right? This is very common when you're working with Julia, that you hear about things that are thousands of times faster than what was done before. And this is essential because, you know, when you have a new capability that is several orders of magnitude better than what you had before, that opens the world up to new kinds of products, new kinds of ideas, new kinds of science. And that is how, you know, we as a civilization make new progress into, you know, solving some of the largest problems we face. I'm going to end with just showcasing some of the, you know, the beautiful packages that Julia has. And of course, these are some of the products that Julia Computing puts together in order to help Julia users in companies and at universities succeed with what they're doing. I'll take any questions if there are.
Yeah, that's great stuff, folks. And just real quick, I had a little thought moments ago, curious to hear your impressions of this, but computation is wasted time, right? Like if it's taking time to compute something, that's wasted time. You want to get right to the results so you can modify your models and get closer to the truth, right, guys? Is that about right?
That's absolutely right. I mean, the longer you wait for your computation, the, you know, that's just, you're doing nothing else, right? You're sort of twiddling your thumbs waiting for the answer to come back.
Yeah,
my old PhD advisor used to have a nice phrase for it that I like to use a lot myself, which is computation at the speed of thought. So that if you could think of something, you should be able to compute it so that you can move on to the next thought just as quickly. You can interact. You have to wait a day or a week or even an hour sometimes for the computation to happen. You're not interacting with your computation and you're not innovating with your computation.
That's exactly right. And I'll just throw this out as well, just so our audience understands. Computer programs are written in languages, just like you speak in a language. So French versus Italian versus Russian versus Hungarian, etc. And different languages aren't just different ways of saying the same things. There are certain nuances to languages like je ne sais quoi, for example, in French, that have a special meaning that don't really translate well. And I think what you've done with Julia, and you set out to do this, one of my old bosses used to say, let's achieve what we're trying to achieve. And I think you've done that. I think if I could explain it, I think what you've done with Julia is you've really harnessed the power of abstraction and of variables. And because you have that large cornucopia of functions that can be used, of operators, that's why you can get 65,000 times the performance. Is that correct?
That's absolutely right. I think that's a very, very nice summary of what Julia is.
Well, this is fascinating stuff, folks. Check these guys out. As I always say, if you're looking for a career, look into data, folks. Look into systems. And what's wonderful is that the folks at Julia are removing the friction from the process. So the fun part of science is when you have ideas, you could test those ideas, see what they do. The unfun part of science is all the boring, tedious stuff. And increasingly, thanks to companies like Google, companies like even Facebook and others, and of course, the folks at Julia Computing, we can just scream right past the boring stuff and get right to the interesting stuff. So thanks so much. You've been listening to another episode of Future Proof. Look these folks up online, Julia Computing. We'll talk to you next time, folks. Take care.